So, welcome to chapter 30, where we delve into the fascinating world of inductance. So, here we'll cover the core principles of inductance and its manifestations in various electrical circuits. So, here we will explore how inductance, a fundamental property of circuits, influences their behavior, particularly in dynamic scenarios. So, get ready to uncover the underlying physics that governs inductive phenomena. So, in this chapter, before we delve into our main discussion, let me introduce to you our learning goals for this chapter. First is how a time varying current in one coil can induce an EMF in a second and unconnected coil. Second is how to relate the induced EMF in a circuit to the rate of change of current in the same circuit. Third is how to calculate the energy stored in a magnetic field. Fourth is how to analyze circuits that include both resistor and inductor. And lastly is why electrical oscillations occur in circuits that include both an inductor and capacitor. Inductance is not merely a theoretical concept, it is a principle at work in numerous everyday applications. So consider a traffic lights for instance. The detection for a vehicle at an intersection often relies on a large coil buried under the road. So this coil carries a current that changes when a car approaches due to the car's conductive materials. So the induced currents in the car then affect the coil, triggering a change in the traffic light. So this is just one example of how inductance plays a vital role in modern technology. So we'll delve deeper into the application as we progress. So here we'll learn about these and other forms of inductance. So mutual inductance describes the interaction between two nearby coils. So here, when the current in one coil changes, it creates a changing in a magnetic flux. So if a second coil is magnetic field, or if the second coil is present in this changing magnetic field, an EMF or the electromotive force is induced in that second coil. So the mutual inductance denoted by big letter M is the proportionally constant that relates the changing current in the one coil to the induced EMF in the other. So here is shown in the screen shown the equation where mathematically expresses this relationship. So the negative sign indicates Land's law, which states that the induced EMF opposes the change in magnetic flux. So to quantify mutual inductance, we use these equations. So the mutual inductance denoted by big letter M can be expressed in terms of the magnetic flux through the coil due to the current in the other. So notice that symmetry here, the mutual inductance is the same regardless of which coil is considered the source and which is considered the receiver of the induced EMF. So the SI unit for mutual inductance is the Henry, which is symbolized by big letter H. So as shown, 1 Henry is equivalent to 1 Weber per ampere or 1 volt second per ampere. So and so on. So understanding these units is crucial for practical calculations. So a practical application of mutual inductance is the wireless toothbrush. So this electric toothbrush makes use of mutual inductance, where exemplified by the electric toothbrush charger shown here. So the base of the charger contains a coil which is connected to an AC power source. This alternating current generates a time-varying magnetic field. So the toothbrush itself contains another coil, so when the toothbrush is placed on the base, so the changing magnetic field from the base induces the EMF. So in the toothbrush coils, which then recharges the battery. So this occurs without any direct electric contact, showcasing the power of mutual inductance. And now let's shift our focus to self-inductance. So unlike mutual inductance, which involves two coils, self-inductance is a property of a single coil. When the current flowing through a coil changes, it creates a changing magnetic flux through itself. This changing flux in turn induces an AMF in the same coil. So this phenomenon is called the self-inductance, and it's quantified by the self-inductance big letter L. So here is the equation in the screen provided. So a coil with a high self-inductance will strongly resist changes in current. So here, if the current I in the coil is changing, the changing flux through the coil induces an EMF in the coil. So inductors plays a crucial role in protecting electrical systems from sudden surges such as those caused by lightning strikes. Lightning strikes can induce enormous voltage spikes in power transmission lines. So here in the screen, potentially damaging sensitive equipment. So to mitigate this, large inductors are incorporated into the transmission system. So inductors oppose rapid changes in current, so the inductor resists the sudden increase in current, effectively smoothing out the surge and protecting downstream components. So this makes inductors essential components in power grids and other high voltage systems. So this use the principle that an inductor opposes and changes rapid. So for comparison, let's briefly revisit resistors. So, unlike inductors, the voltage across a resistor is directly proportional to the current flowing through it. So, as described by the Ohm's law, V sub A, AB is equal to IR. So, the voltage and current are instant related. So, here the resistor dissipates energy as heat, while an ideal inductor stores energy in its magnetic field. So here is the graph below. When you have a resistor with the current flowing from A to B, so the potential drops from A to B. So for the potential across an inductor with constant current, the potential difference across an inductor depends on the rate of change of the current. So when you have an inductor with constant current flowing from A to B, there is no potential energy. So here is the I constant. dI is equal to, or dI over dt is equal to 0. Well, V sub AB is equal to L over L di over dt is equal to 0. So in this special case where the current through an inductor is constant, the rate of change of the current di over dt is 0. So consequently, the voltage across the inductor V sub AB is also 0. It's because an inductor behaves like a short circuit under the DC or the direct current conditions after the transient effects have died down. So potential across an inductor with increasing current. So when the current through an inductor is increasing, di over dt is positive. This means that the voltage across the inductor V sub AB is also a positive. So the inductor opposes the increasing current, acting as a temporary source of AMF that resists the change. So when you have an inductor with increasing current flowing from A to B, so the potential drops from A to B. So increasing di over dt greater than 0. So the potential difference across an inductor, it depends on the rate of the change of the current. So di over dt is greater than 0. So potential across an inductor with decreasing current. So the potential difference across an inductor depends on the rate of change of the current. So So conversely, when the current through an inductor is decreasing, di over dt is negative. So this results in a negative voltage across the inductor, V sub AB. So in this case, the inductor acts to maintain the current it and it becomes a temporary source of AMF that tries to prevent the current from decreasing. So current decreasing di over dt is less than 0. It opposites by the previous slide. So V sub AB is equal to L di over dt is less than 0. Great is greater than or is less than 0. So a key characteristics of inductors as their ability to store energy in the magnetic field in their magnetic field they create. So the amount of energy stored is given by this equation. U is equal to L represents the inductance integral from initial value of instantaneous current to final value is equal to 1/2 inductance squared or the final current squared. So this stored energy can be released back into the circuit when the current decreases. It make inductors useful for applications like power conditioning and energy storage. Now let's analyze circuits containing both resistors and inductors, known as the RL circuits. So these circuits exhibit time-dependent behavior due to the inductor's opposition to changes in current. So the diagram shows a typical RL circuit with a switch that can connect the circuit to a voltage source or short it. So here we will examine how the current changes over time when the switch is closed or open. So closing switch connects the RL combination in series with the source of EMF while closing switch 2 while opening switch 1 disconnects the combinations from the source. So current decay in an RL circuit. So suppose there is an initial current running through the resistor and inductor shown here. So at time t is equal to 0, we close the switch 2 by passing the battery, which is not shown in the diagram. So similarly, when the switch is open or moved to position that shorts the voltage source, the current in the RL circuit doesn't drop to zero. It's because it instead it decays exponentially with the same time constant is equal to L over R. So the inductor releases the energy stored in its magnetic field, which sustaining the current for a short period of time. So the larger the inductance or the smaller the resistance, the slower the current it decays. So as you can see here in our presentation, switch 2 is closed at t and t is equal to 0. So current decay in an RL circuit. So suppose there is an initial current running through the resistor and inductor shown here. So at time t is equal to 0, we close the switch 2 by passing the battery, which is not shown in the diagram. So similarly, when the switch is open or moved to position that shorts the voltage source, the current in the RL circuit doesn't drop to zero. It's because it instead it decays exponentially with the same time constant is equal to L over R. So the inductor releases the energy stored in its magnetic field, which sustaining the current for a short period of time. So the larger the inductance or the smaller the resistance, the slower the current it decays. So as you can see here in our presentation, switch 2 is closed at t and t is equal to 0. So next in step 2, the capacitor begins to discharge through the inductor. As the capacitor discharges, the current increases and the magnetic field builds up around the inductor. So energy is now being transferred from the capacitor's electric field to the inductor's magnetic field. So when the capacitor is fully discharged, all the energy is stored in the inductor's magnetic field and the current reaches its maximum value. So here as the capacitor discharges, the current increases, but the rate of change of the current is decreases. So when the capacitor potential becomes zero, so the induced AMF is also a zero, and the current has a max and its maximum value of initial IN. So the LC circuit is step 3. Although the capacitor was completely discharged in step 2, the current persists and capacitor begins to charge with polarity opposite to that in the initial state. So eventually, the current in the magnetic field reach zero and the capacitor has been charged in the sense opposite to its initial polarity. So the current continues to flow even after the capacitor is fully discharged. So this current now charges the capacitor with the opposite polarity. So as the capacitor charges, the current decreases and the magnetic field around the inductor collapses. So eventually, the current reaches zero and the capacitor is fully charged with the opposite polarity, and all the energy is now stored in the capacitor's electric field again. So for the last step, the process now repeats in the reverse direction a little later. So the capacitor has again discharged, and there is a current in the inductor in the opposite direction. So shown in this situation, the capacitor has completely discharged and the current is maximal and the circuit's energy is all stored in the magnetic field. So still later, the capacitor charge returns to its original value and the whole process repeats and return to step number one. So this continuous transfer of energy between the capacitor and the inductor creates a electrical oscillation. So in an ideal LC circuit, this oscillation would continue indefinitely, but however, in real circuits, resistance will cause the oscillations to gradually decay over time. So, electrical and mechanical oscillations analogies. So, to further illustrate the connection between the electrical and mechanical oscillations, let's examine direct analogy between an LC circuit and a mass spring system. So, in a mass spring system, the kinetic energy of the mass corresponds to the magnetic energy stored in the inductor, while the potential energy of the spring corresponds to the electric energy stored in the capacitor. So the mass, which is denoted by small letter m, is analogous to the inductance L, and the spring constant K is analogous to the inverse of the capacitance 1 over capacitors. So the equations governing the energy, velocity per current, and displacement per charge are strikingly similar, but they differ only in the symbols used to represent the physical quantities. So this analogy is provides a powerful tool for understanding the behavior of LC circuits. So by drawing upon our intuition about mechanical systems, the angular frequency of oscillations, whether mechanical or electrical, is determined by the square root of the ratio by the stiffness, K or 1 over C to the inertia M or L. And now, let's now delve deeper into a mathematical description of electrical oscillations in an LC circuit. So, by applying Kirchhoff's loop rule, we can derive a. So now let's introduce a third component. resistance. So the series circuit consists of an inductor, capacitor, and resistor, which is connected in a series form. So the presence of resistance introduces damping to the oscillations. So we begin by changing the capacitor. When the switch is moved, the capacitor discharges through the inductor and resistor. The resistor dissipates the energy as heat, reducing the amplitude of the oscillations over time. So the behavior of this circuit is more complex than that of ideal LC circuit, but it more accurately reflects a real-world circuits where resistance is always present. So the AMF sources changes the capacitor initially. So the LRC circuit exhibits damped harmonic motion. So the charge on the capacitor still oscillates, but the amplitude of the oscillations decreases exponentially with time. So this decay is due to the energy dissipated by the resistor. So the angular frequency of the damped oscillations denoted as here is given by the equation that attached on our screen. So notice that the presence of resistance reduces the angular frequency compared to the undamped LC circuit. So if the resistance is large enough, the term inside the square root becomes negative and the oscillation ceases altogether. So in this case, the circuit is said to be overdamped. So here if r squared over 4l squared is equal to 1 over LC, the circuit is critically damped and the charge returns to zero as quickly as possible without oscillating. So the condition shown on this slide is for an underdamped circuit where oscillations occur but decay over time. And the behavior of the LRC circuit is crucial to understanding many real-world applications such as tune, circuit radius, and television.